All right, we're recording. There's our calculator if we need it. Okay, did I? Yeah, I already took roll. Good. If anybody walks in late, I'll have to mark them as here, but. Okay, so this is chapter 6. This is continuous distributions. In chapter 5, we talked about discrete and continuous distributions. Chapter 5 is about discrete distributions. Flipping a coin, rolling a die. You can't get the number a half when you roll a die. But continuous distributions, these are measurements. And this is a special type of continuous distribution, is the normal distribution. And the normal distribution is bell-shaped, with the highest point over the mean, mu. So the mean is right in the center, and the curve is symmetrical. About the vertical line through mu, and the curve approaches the horizontal axis but never crosses or touches it. It's showing like it's touching here, but it's really not. It's getting closer and closer and closer, but it doesn't touch it. And we find probabilities with continuous distributions. We find probabilities as areas under the curve. Okay, this is chapter 6. And sometimes people struggle with the chapters 4 and 5, and they can get to chapter 6. Chapter 6, I let you use the calculator shortcuts. If you know how to use your calculator, you can do chapter 6. But you do need to understand it and know what to put in your calculator and what to use. So we're recalling from chapter 3 that the standard deviation it's a statistic that tells you how tightly all the various examples are clustered around the mean in a set of data. And when we have a bell curve, the normal distribution like this, when the examples are tightly bunched together and the bell-shaped curve is steep, the standard deviation is small. So this picture here that's tall, narrow and tall, that sigma is small. When the examples are spread apart and the bell-shaped curve is relatively flat, the standard deviation is large. So this picture here, okay, we do it in orange. This has sigma is large, the standard deviation. And these are distributions, so I'm using distribution symbols. Sigma is the symbol for the standard deviation of the distribution. So, small, here's a picture of that, and then the other picture is this picture in black here. This is the standard normal curve. And sigma equals 1. So there's sigma small, sigma's large, and that's the standard normal curve. Sigma is 1. And so for most measurements, if you made a histogram with them and normalized it and smoothed it out and drew a curve, it would be a normal distribution. Most measurements are like that. So so every normal curve, these all have an area of 1 underneath them. The area under the curve equals 1. And we find probabilities as areas under the curve, so all probabilities will be between 0 and 1. And we learned that that had to be true. So we will find probabilities, so our probabilities will be between 0 and 1. All of those will be, but it's not a discrete distribution because we can take on any decimal number in here. And we'll find as areas under the curve. Well, so for every normal curve, maybe I should shut off one of these lights. Every normal curve has the same shape. And the area is 1. But this is the empirical rule, and it works on all bell-shaped curves. The empirical the empirical rule, and it works on bell-shaped distributions, normal, is that approximately 68% of the data lie within 1 standard deviation of the mean, and approximately 95% of the data lie within 2 standard deviations of the mean, and approximately 99.7% of the data lie within 3 standard deviations of the mean. So you've got your picture at the top of the page. We could mark that one up with these numbers. So we've got this distance here is sigma. And these are, between here and here is mu plus sigma, mu minus sigma. That's plus or minus 1. So this area is for every normal curve between positive 1 standard deviation above the mean and 1 standard deviation below is about 68%, or 0.68. What? Oh, the percent or the?
Well, no, I'm saying like you take an area under a curve.
Oh, yes,
You're not
exactly.
finding
So if you were doing this calculus-based statistics, you would actually take it into this.
Okay.
Yes. Yeah, but those of you that didn't have calculus yet, we're just gonna use the table. And we have a normal function on the calculator that will give you that area. Okay? And so we don't have to use any of this, but we could. Okay. So, and then between here and here, which is mu plus 2 standard deviations, mu minus 2 standard deviations, that area in purple here is 95%. And then if you go to 3 places, then that's the 99.7, and it's getting hard to read my graph. But, and you can, I have an old slideshow that shows, you can figure out all these little, exactly how much is in each little section. We find areas under the curve, and so, like the empirical rule, the shaded area is the 95%. So if you want to find the area in this little section and this little section, you take 95% minus 68% is 27% divided by 2, and you get 13.5% in these two. This one is 13.5, and this little area is 13.5. And then if you do 99.7 minus 95 and divide it by 2, you get 2.35%. And you can use that to make sure your answers make sense. So you can do the same computations. Oh, I've done it here. 99.7% minus 95. Get rid of the calculator. Oh, that didn't help. I could make this, I think it makes it blurry when I do this. No, it didn't. Okay, then we can make it. So, we had 99.7 minus 95 gives you 4.7. Divide that by 2, you get 2.35%. And if you take the 68%, divide it by 2, you get 34%. So if I make that a little bigger, you can see this little area has 2.35%, 13.5, 34, 34. And so you can use that to make sure your answers are making sense. That's all from the empirical rule. Okay. So we could actually, I could write those down. This is 2.35%. I don't know if you can read that. And this is 13.5. Yeah. This is halfway here is 34%. And then it would be the same on the other half. Those percentages can be used, and the area under the curve equals 1 or 100%. So half the curve will be exactly 50%. So this half is 50, this half is 50. So it equals the whole area under the whole curve equals 100%, or 1. So we'll usually write these as decimals then. Okay, so that's the empirical rule, and you can use it to work a problem. Here's an example. We can just use this empirical rule if they give us things. And we want to go ahead and draw the picture. And there's a nice picture drawn on the next page right behind this, so I can copy that. Then you make about 3 marks each way. All right, so let's read the problem. Distributions are populations, so it's normally distributed, so it's a distribution, so it's a population. So our mean, we're going to use mu, is 1100 hours. The life of a particular light bulb is normally distributed with a mean of 1100 hours. So the mean goes right in the middle. when it's normally distributed. We put the mean in the middle. And it has a standard deviation of 100 hours. So we're going to add sigma going up, so 1100 plus 100 is 1200. Another 100 is 1300 and 1400. These are our x's, the horizontal axis. And it's in hours. And then we subtract 100 going down. So from the mean, we subtract 1 standard deviation, we get 1,000. We subtract 100, or 1 standard deviation, we get 900, and then 800. And I do require that you draw your curves and you label your axis and and you shade what you're looking for. So it says, draw a bell-shaped curve to illustrate these statistics. So we've drawn this. So what's the probability? So now we're going to ask for a probability that a light bulb of this type will last between 1,000 and 1,200 hours. So the notation is probability that X is between 1,000 and 1,200 hours. That's between. And it doesn't matter the area for 1 point. Let's draw this. So this is 1,000 and this is 1,200. This is the area we're looking for. And it doesn't matter if we have an inclusive or exclusive. The area of 1 point, because the width is 0, will be 0. So we're talking about in discrete distributions, it matters whether it says less than or less than or equal, or greater than equal. In this case, it doesn't, because we're finding probabilities as areas under the curve, and the area under the curve at 1,200 at 1 point has 0 width. So 0 times anything, make a little rectangle out of it, is 0. So it doesn't matter. So, but anyway, so we look at that, and from our picture, can you tell that we've shaded in from -1 standard deviation to +1 standard deviation? What?
So if you're looking at 1,000 to 1,200, you'd have to just go, right?
Yeah, but you'd have to use the formula for the normal curve, I guess. Yeah. But this is by the empirical rule between 1,000 and 1,200 is 68%. And we change that to decimal. So we find, using the empirical rule, that this is approximately 0.68. Okay, so that's the probability. .68. So, and I didn't write this down, but on my notes I have, this is our mean plus 1 standard deviation, mean plus 2, mean plus 3, the mean minus 1, etc. That's how I got those numbers. All right, well, before calculators, what we recognized, and here's a picture from a slideshow, that any normal curve will, no matter if it's tall and narrow or short and squat, will have the same area. So this normal curve has 68% between -1 standard deviation and +1. This normal curve also has 68%. So the areas are always going to be equal. And so this is the time before calculators. So they came up with a standard normal curve. The standard normal curve. So it does say the word standard. Has a mean of 0 and a standard deviation of 1. And we call the horizontal axis then Z. And we call these the Z-scores on the horizontal axis. And what we used to do is we used to use tables. And you could convert all your X's to Z's and you'd look in the table and find the areas. Because we didn't have calculators. Now I don't make you use tables. You just use the calculator. But if you, sometimes you have to still use tables if you go on to take business statistics. But it's not hard to use tables either. But okay, so the Z-score tells the number of standard deviations between the original measurement and the mean. And we're going to learn how to convert between a normal distribution and a standard normal distribution once we understand how to calculate the area under the curve. So this is the directions for calculating an area under the curve. We're going to use normal CDF under second variables because those are distributions. The normal CDF function requires you enter a left boundary and a right boundary separated by a comma. Or if you have the stat wizard, you don't have to put that. It'll prompt you for those. So if you put in the comma in, the boundaries that you use will depend on the problem you're working on. And it's very important you draw a picture of the area you're trying to find before you use your calculator to find the area. In fact, this is required as part of your points. If you just give me answers and no probability notation, no pictures, and I even have pictures already on my test, so you're not going to get all your credit. And here's some examples. So we're going to do some examples. Now, so I think, yeah, here's the example. So when we're finding the probability under the standard normal curve, it'll use Z. That means it's a standard normal curve. So if it uses Z, means the standard normal curve. And that means that the mean is 0 and the standard deviation is 1. So you always mark the curve off on these with 0, 1, 2, 3. Minus 1, minus 2, minus 3. And that's your Z's. So if you want to find less than 1.27, means less than means it's an area to the left. .27 would be about here, so I just draw a vertical line and write 1.27. And then because we're looking for the area to the left, you shade the area to the left. You can shade it all in, or however you want to shade it, but it has to be shaded. And it's going to negative infinity, so you might want to, and we use just a large negative number like 1,000, or for Z we can use a negative 100, but I'm just going to use 1,000. So, all right, so then we're going to use our calculator. we're gonna use a calculator to find that. Here's the command. It's normal CDF. Sorry, the left bound is negative 1,000. The right bound is 1.27. And here we're gonna do it in our calculator. So what kind of area would we expect? Well, from here, this area should be 0.5. From minus infinity to 0 will be half your curve, so it'll be 0.5. And this area will be 0.34. So our answer, or our area, will be greater than 0.84. I add those together. I'm going to get an answer greater than 0.84. That's using the empirical rule and the fact that it's a normal curve to figure out what kind of answer do I expect to get. Whoops, where'd that go? Okay, let's turn it on. Clear. Okay, no, not stat, clear. Second, variables, because that's distribution. And we always use the CDF function, so go down to number 2. I don't know why the PDF function's there. Normal CDF. It's just lower limit, upper limit, and that gives you the area under a standard normal curve. And then you put in negative 1,000. Don't use a subtraction sign. You have to use a negative in front of the 1,000. Otherwise you get an error. Comma 1.27. And then we're going to round to 4 decimal places. So that the answer is 0.8. I'm going to write 5 places down. 0.89795. We look at the 5 means you go up to 10, and that brings that up to 8. So it's 0.8980. That's our area. You can write it down here. I boxed it in. Okay. That's how you find less than. You go, it's the lower limit. So what we're doing on these are all Z, finding probabilities of Z under the standard normal curve. We're finding all these probabilities using normal CDF, the lower limit of Z, whoops, let me get rid of that calculator again. The lower limit of Z, comma, the upper limit of Z. If you're using Z, you don't put anything else, you leave the mean and standard deviation at 0 and 1, or leave it off. Okay, so these will all be Z. So this is Z. This is the first step. So see if you can do the next one. You'll do the next one. Mark it, shade and label, and see if you can find that next area. And okay. So did you get that one? Let's see what you got. and we can write NCDF to shorten it. It's gonna be negative 1,000, because we're doing less than, to negative 2.71. This is minus 3, minus 2, minus 1, 0, 1, 2, 3, because it's Z on the horizontal axis. So we have numbers on a horizontal axis and we have areas. Minus 2.71 is about here. So we're only looking for this tiny area. This should be very small. It should be less than 0.0235, 2.35%. Put it in your calculator. You can recall your last entry, second enter, and just change this to negative 2.71. And round to 4 places, you get 0.0034. And that's how you find probabilities for less than. It does help. Some people need to do this, is to draw minus infinity and put a large negative number here, like negative 1,000. This is your lower limit. This is your upper limit. This was your lower, let me get the calculator out of the way again. So, if you think you're going to be tempted to put negative 3 for a lower limit, that's not right. This is lower, the upper. That's how you do it in the calculator. And when you're doing less than, you'll always have negative 1,000 or negative infinity for a lower boundary. All right, now let's do between two numbers. Well, that's even easier on the calculator. The table you could read this right off the table, but I don't even, unless anybody wants to see the table, I don't usually even show it to them. Although I give you the table for other reasons, but. Okay, so this is find the probability that Z is between 0 and 1.24. So again, this is the standard normal curve. The mean is 0, and the standard deviation is 1, so you add 1 going up, and you got about 3 marks each way. And if I want to do it, use a different color between, so make a line at 0, and I make a line at, and I can even put 0 down here, about 1.24. And then you shade between there. This is your area that you're looking for. And what is it going to be greater than? Well, it better be greater than 0.34 by the empirical rule. Half of the 68% is 0.34, and that would be this area, and you got more because you went beyond 1. So you're going to use normal CDF, and I'll shorten it, NCDF. The lower limit here is 0, and the upper limit is 1.24. And that's what you put in. So we bring the calculator back up. Second distribution, normal CDF, 0, 1.24. And we get 0.3925. And that's your answer, but labeling your graph, shading, that's all part of your points. Probability notation, if I asked you in words, that would be part of your points. Okay. All right, see if you can do the next one, between two numbers. Well, you should always ask, does my answer make sense? Okay. See if you can get the next one. Okay, now these with greater than sign, well, that's not, we didn't do this. Probably supposed to be greater than. Oh, well. All right, I guess it's just another lesson. You got that one right. Okay. But you're gonna want 'em, you're gonna have to write and shade and all that. All right, so, again, this is Z. If you don't write, you don't label Z out there, that's okay. Horizontal axis always looks like this, about 3 marks each way. All right, from minus 2.34 to 1.57, and then you shade all of this. Okay? That is going to be most of the curve. If you get a number that's less than half, you know it's wrong. But it's just, you're just going to put in normal CDF, negative 2.34, comma 1.57. Oh. And if you do that, second distribution, normal CDF is number 2, negative 2.34, comma 1.57. And you get 0.9322 to 4 places. All right, what are the common mistakes? You forget a negative sign. If you leave a negative sign out, or you put a subtraction sign instead of a negative. If you put a subtraction sign instead of a negative, your calculator's going to tell you quit. Calculator's always saying that. It's because you need, it's particular. You need to have a negative sign up here. The second enter, that's a negative sign. But if you accidentally leave the negative sign off, you're going to get that. What's that? That's the complement of the area you actually want. That's 1 minus the area that you want. So be careful with your negative signs. If you get a negative area, what does that mean? Can you have negative probability? No. But what happened, why did we get a negative here, is because we went from 2.34 to 1.57. We went in a negative direction on the horizontal axis. That's why it thinks it's a negative area. We always want to put the smaller number on the left, the bigger number on the right. But I purposely, this is the wrong answer to this problem. I purposely left off the negative sign. Okay? Just showing you what can happen. So, if you're at home doing your math lab and you're getting calculators saying crazy stuff, well, you're probably typing it in wrong. So you need to put it in smaller number, bigger number. Be careful to use a negative there, not a subtraction sign. Okay. All right, and between minus 3 and 3, by the empirical rule, this should be approximately 99.7% or 0.997. But if I want my 4th decimal place, then you're going to put that in your calculator, minus 3 you can go from minus 3 to 3, shade all that stuff in. It's normal CDF minus 3 to 3. Put that in your calculator. Second distribution, number 2, normal CDF, minus 3, comma 3. And that last digit is a 3. Okay, we wanted 4 decimal places. We were gonna want 4 decimal places unless, you know, it's using the empirical rule, then we only take 2 or 3. Okay, and then what do we do for greater than? So again, we mark off our axis. Greater than 2.39, 2.39 is this tiny area. It better be tiny. We're going to go from 2.39 to positive infinity, or a large number like 1,000. Some people use 1E99 for that. We don't need to be that exact. We only need 4 decimal places. So we don't need to put in 1 times 10 to the 99. We can put in 1,000. So this is normal CDF. The lower limit this time is the 2.39, left to right, and the upper limit is 1,000. So that's how we do greater than. This is our lower value of Z. This is our upper value of Z. Second distribution, normal CDF, 2.39, comma, 1,000. And you get 0.0084. Okay, greater than negative 1.43, so see if you can do that one. That's another greater than sign. Okay, so negative 1.43, comma, 1,000. 0.9236. And did that make sense for the amount of area we had shaded? Yes. And usually, if you make a mistake, you're going to get the unshaded area. If you get something less than a half, you know it's wrong. You can tell that you can tell that the area needs to be greater than 0.84, but you know, we got half here and 0.34 here, so it's greater than 0.84 by the empirical rule. And that's it. And then the last one, if you do it, you should get 0.9975. That's less than again. So see if you get 0.9975. Shade and label. And we'll be on the inverse normal distribution as soon as we take a break. So we can take a break. Yeah. Just watch Peggy, because I think that worksheet will be good, because we're going to start with the inverse norm next. That worksheet is simply using, we're doing it on the next page, and all the filled in notes are posted too. This is actually an easier section at first, but we add to it. Okay, we keep adding to it. All right. Is greater than 2.81, gosh, it's this tiny area, goes to positive infinity, 1,000. So it's normal CDF, 2.81 to 1,000. Oh, you're right. It's a less than sign, negative 1,000 to 2.81, and we needed to shade to the left. So don't make that mistake. There we go. It's a less than sign, and it's less than, we're going from negative infinity, negative 1,000 to 2.81. Okay. So when it's greater than, you're gonna go from the number to positive infinity. When it's less than, you're gonna go from negative infinity to the number, and we just use a negative 1,000, and positive 1,000. And then when it's between, it's even easier on the calculator, just put the two numbers in. Between is the easiest. If you have to use the table, it's more complicated. But if you understand what you're looking for, it's not that difficult, but I don't make you use the table. I don't even teach the table anymore. Okay, that table is for before calculator. Okay, we're gonna pause it, we're gonna